Okay, so now I wanted to explore the difference of squares in a few examples, a little bit more detail. Again, here's the map for the difference of squares. A squared minus b squared is equal to the quantity a minus b times the quantity a plus b. Let's just check out that relationship first, and then I'll show some examples. So here's a quick check just to see if this map is correct. And how could I check this? Well, I can multiply these, and if I get the difference of squares, then I know it's okay. A minus b times a plus b. So we're going to take a times a, and then a times b, follow that with negative b times a and negative b times b, which looks like a squared for the first term plus ab. The next one I get minus ba, or I could call that a minus ab. Remember that in multiplication we can flip these numbers around, generally speaking for now. And then negative b times b over here is negative b squared. Notice that plus ab minus ab adds up to 0, therefore we obtain a squared minus b squared, which we should. So this map up here checks out. Okay, I'll put a box around this. This is the rule that we're going to use. That's kind of the general pattern to know when looking at examples. So let's take a look at, for example, x squared minus 9. This may or may not be a difference of squares. So the first thing we need to look at is, are these two things squares indeed? Now, certainly x squared, it is x squared, quantity squared. How about 9? Well, that's 3 squared. So if I wanted to match it up to my map, I could say a is equal to x, because x is the thing that's being squared to give you the first term. B is equal to 3, because 3 is the thing that's being squared to give 9. So if I follow the pattern up there, I can say that this must factor to x minus 3 times x plus 3, and that's it. There's our factored result. You can check it by remultiplying, although we've already done that in the general case, so it must work for this case as well. Let's take a look at a few more examples. How about, what if we had 4x squared minus y squared? So what is being squared to give us that first term is the question. And we can say that it is 2x. A is equal to 2x. How come? Well, we could check that. Suppose we were going to square 2x. How would that come out? That's 2x times 2x, which comes out as 4x squared. So indeed, a is 2x. From the y squared, clearly y is equal to b, because if we square it, we get y squared. Therefore, I can say that this must factor to 2x minus y times 2x plus y. And I should say, as a matter of practical operation, I don't really always write this a and the b. In fact, I stop doing it as soon as I'm very comfortable with the difference of squares and I've memorized it, I know how it works. Really all I start looking for is the what's being squared for these two terms, and immediately I know those are my terms that go in the binomials. Let me give one more example of the difference of squares that may not immediately present itself. Suppose we had 16x squared minus 81y to the fourth, and actually I don't want this to be squared. I'm going to erase that. I'm going to smear it around until it's erased properly. There we go. Okay, what I meant was 16x to the fourth minus 81y to the fourth, and it doesn't perhaps immediately look like a difference of squares. Certainly there's a difference, but these are to the fourth power. However, I can represent these as something squared, and indeed, every time you have an even power here, you can represent those even powers as something squared. The numbers, though, you also have to be careful with and see if those are squares. So let me cut to the chase here. Notice that if I say a is equal to 4x squared, then indeed 16x to the fourth is a squared. Notice if I just wanted to check that, what is a squared? I would say parentheses 4x squared squared, okay? Which is 4x squared times 4x squared, which gives you 16x to the fourth. So yeah, that works to say that it is something squared. Likewise, b is equal to, 81 is a perfect square, so I know that I can put a 9 here, because 9 squared is 81. And I can also say y squared, because y squared squared is y to the fourth. If I did the same thing here, I would find that indeed I come up with that number. So what that means is I can start, I need a little bit more space, so I'm going to erase this. I can start by saying 16x to the fourth minus y to the fourth is equal to, parentheses, 4x squared minus 9y squared times 4x squared plus 9y squared. Now what we should do at this point is look for other things we can factor. And notice that this guy right here, 4x squared minus 9x squared, this in and of itself is a difference of squares. The one on the right is a sum of squares. So the difference of squares I can factor. I'm going to factor this, and let's look at that first. That gives me 2x minus 3y times 2x plus 3y. I'm just going to carry this whole thing down. I still have 4x squared plus 9y squared. And so notice how this thing broke out into two different binomials. So in the end so far, I can say that we have 3 real binomial factors. And so if your course does not deal with the imaginary unit, then this is where you're going to stop. You're going to call that the factored result of the above. If your course does use the imaginary units, then you're going to take this one more step, because this right here is a sum of squares. And I'll go into that a little bit more detail in the next video, but let me just expand it using that. I'll put it in pink here. I still have my 2x minus 3y times 2x plus 3y. That's these two guys. But then that sum of squares factors into 2x plus 3y I times 2x minus 3y I. And what you're probably noticing is that the sum of squares and the difference of squares really follows the same pattern, and it does. But with the sum of squares, you have to add that imaginary unit there, otherwise it's not going to work. So let me move on to talk about the sum of squares. And you can skip that video if your course doesn't use the sum of squares, or if you just don't care. But I encourage you to watch it anyway, because why not? It's fun to learn.